Assalamualaikum and good day everyone. We are from Group 1, Section 2 for the course DELE 2113 Electrical Machine. We would like to present about our topic title, Transformer for Solar PV Integration. Okay, for the introduction of this topic, the rapid growth of large-scale solar PV creates technical challenges for power system in regions such as Ontario and South Africa. Distribution transformers are critical for grid-connected PV but are affected by inverter-generated harmonics, which increase losses, temperature rise, and insulation aging. In South Africa, large-scale PV deployment has increased the need for specialized high-capacity transformer to handle renewable energy integration reliably. Overall, successful large-scale PV integration requires improved transformer design, advanced power electronics, and proper grid planning to ensure reliable, efficient, and sustainable power systems.
IEEE Standards. IEEE Standard 1547. IEEE Standard 1547 governs the interconnection of distributed energy resources such as solar PV to power system. It specifies requirements for voltage and frequency regulation, power quality, protection, and write-off capability. When focused on DER operation, it indirectly affects distribution transformers by influencing voltage levels, loading conditions, and long-term reliability in high DER networks. IEEE Standard C 57.91. IEEE Standard C 57.91 provides guidelines for safe loading of oil-immersed transformers based on thermal limits and insulation aging. It explains the impact of temperature rise and overload on transformers' lifespan and is especially important for PV application where inverter-generated harmonics increase losses and thermal stress.
I'm going to talk about literature review. A widely cited study by Yildirim and Fuchs investigated transformer derating under non-sinusoidal harmonic loading conditions. The research showed that the eddy current losses in transformer windings increased approximately with the square of harmonic frequency, causing higher order harmonics to contribute significantly to heating. Experimental results on the single-phase transformer demonstrated that the real power derating is greater than the apparent power of derating for the same total harmonic distortion, which is called THD. The study also found that derating calculated using the harmonic loss factor FHL closely measured transformer behavior when eddy current and core losses were properly considered. Additionally, stray losses in transformer metallic components were found to be frequency dependent, influencing overall thermal performance. The study highlights the importance of harmonic-based derating methods to ensure reliable transformer operation and prevent premature installation aging in systems with nonlinear loads.
A transformer works by mutual induction to transfer electrical energy and change voltage level. Normally, the main losses in a transformer come from copper losses and core losses. When distributed energy resources like solar PV are connected to the grid, inverter system produce non-sinusoidal current, also known as harmonics. These harmonics can affect voltage quality and increase transformer loading. Standards such as IEE 1547 to 2018 help control this effect by setting requirements for voltage regulation, reactive power support, and system stability.
Third, impact of harmonics on transformers. Non-linear loads such as PV inverters generate harmonic currents that distort voltage waveform and increase transformer heating. Key harmonic effects include increased copper losses due to harmonic currents, higher eddy current and stray losses that rise with frequency, elevated temperatures leading to accelerated insulation aging. Harmonic distortion is commonly measured using total harmonic distortion. This is the formula of total harmonic distortion. Number 4, Transformer Loading Guidelines and Harmonic Derating. Transformer Loading Guidelines. IEEE Standard C5791 provide guidelines for safe transformer loading based on thermal limits, insulation aging, top oil temperature, and winding hotspot temperature. It includes thermal model to calculate allowable loading under both sinusoidal and non-sinusoidal conditions, helping engineers estimate transformer life and permissible loading in DER integration systems. Transformer derating under harmonic. IEEE Standard C57110 addresses transformer operation under harmonic reach loads by introducing the harmonic loss factor FHL, which quantifies additional winding heating caused by harmonic currents compared to the fundamental frequency.
This slide explains the transformer derating procedure under non-sinusoidal loading conditions. When harmonic are present, transformer losses increase, especially copper losses, stray losses, and winding eddy current losses. To prevent overheating, the transformer must be derated. The equation shown is used to calculate the maximum allowable per unit load current, taking into account the rated load loss, harmonic loss factor, and eddy current losses. This ensures that harmonic induced heating stay within safe design limits and protects the transformer from thermal damage.
Number 7. Empirical findings and literature support. Experimental studies including IEEE research confirm that high harmonic content increases transformer eddy current and stray losses, making the rating necessary to maintain reliability. Other studies show that PV-induced harmonics and rise transformers hotspot temperatures by 8 until 12 degrees Celsius, accelerating insulation aging and reducing lifespans. Number 8. Global PV Integration Challenge. High PV penetration introduce challenges such as reverse power flow, voltage fluctuation, and protection coordination issues. Advanced solutions like modular PV system, multi-level converters, and solid-state transformers help mitigate harmonics, improve power quality, and ensure safe transformers operation.
Okay, now for case study, real-world application. First, conveyor system at a coal mine. In automated coal mining operation, conveyor belt systems are essential for transporting coal from extraction point to processing plants. The process flow is as follows. Coal is extracted from open cast pits where it is mined from the earth. Second, the raw coal is fed onto conveyor belts and transported to a processing area where it is washed and screened to meet quality standards. Third, the processed coal is stockpiled before being transferred onto another conveyor system. Finally, coal is loaded onto train carriers, this time for nearby power stations.
Distribution transformer in a high PV network. In high PV residential network, solar inverters introduce harmonic currents, especially odd order harmonics. This harmonic increase transformer losses such as low load, eddy current, and stray losses, which raise the hottest spot temperature. As a result, transformers may overheat and experience faster insulation aging. To maintain reliability, utilities use K-rated transformer and install harmonic filters. Research showed that under high harmonic conditions, transformer may need to be derated by about 15 to 25%. Technical implications. Both case studies show that nonlinear loads such as industrial VSD and solar PV inverters significantly affect transformer performance. Harmonic current increase thermal stress by raising copper and eddy current losses, leading to higher oil and hot spot temperature. This harmony also accelerates insulation aging, reducing transformer lifespan. Therefore, proper transformer sizing using K factor ratings and harmony loss factor is essential to ensure safe operation.
Now, here's about engineering calculations for total harmonic distortion THD calculation. This section presents sample engineering calculation to demonstrate the impact of harmonic currents on transformer performance under non-linear loading conditions, such as those introduced by solar PV inverters and variable speed drives (VSDs). So these calculations are based on standard formulas discussed earlier and are aligned with IEEE standard C57.91 and IEEE standard C57.110 guidelines. So let's say there's given fundamental current, which is I1 equals 100 ampere, and fifth harmonic current, which is I5, 20 ampere, and seventh harmonic current, I7 equals 15 ampere. So the formula of this THD is basically root of fifth harmonic current plus I7 current, which is harmonic 7th current. So the root of there divided by fundamental current, which is 100 ampere. So when you put on calculation, you can actually get the calculation, which is 25%. Okay. This result shows that the transformer is subjected to high harmonic current, which increases losses and heating. So now here's about harmonic loss factor, FHL. So assuming harmonic spectrum, okay, harmonic order is basically 157. Let's say there's 157, which is the order of the harmonic. So we got per unit current 1.0 and 0.2 and 0.15. So the formula is basically FHL equals summation of the harmonic order squared times per unit current squared. So when you see the calculation on the slide, you can actually see how we calculate the FHL. So we took the first harmonic order and we times with the per unit current to get the FHL. Okay, that is basically the harmonic loss factor. So for the K factor, we got the K equals summation of the harmonic order squared times per unit current squared again. So it's basically the same process, but we use for K factor. So the K factor is basically indicates the additional transformer heating will occur during non-linear loading.
Number 4. Transformer derating. A 1600 kV ampere transformer with an allowable per unit loading of 0.77 must be derated to 1232 kV ampere to prevent excessive temperature rise. Number 5. Maximum allowable load current. With a rate current of 1680 ampere and a per unit limit of 0.77, the maximum allowable current is 1293 ampere. Exceeding this limit may accelerate insulation aging. sustainability and environmental impact. Number 1. Transformer thermal egging. Operating transformers above recommended temperature limits accelerates insulating egging, reducing transformer lifespans and increasing the need for replacement. IEEE standard C57.91. Number 2. Transformer losses and efficiency. Higher transformer loading leads to increased losses and higher hotspot temperatures, reducing efficiency and increasing energy loss. IEEE standard C57.91. Number 3. Renewable energy interconnection. IEEE standard 1547 ensures safe and reliable integration of renewable energy sources such as solar PV, supporting sustainable and low carbon power system. Number 4. Harmonics and environmental impact. Harmonic current increase transformer eddy current losses and temperature rise, lowering efficiency and indirectly increasing environmental impact due to higher energy losses and equipment replacement.
So last but not least, we're going to talk about the conclusion of our topic. So the increasing use of solar PV systems and non-linear loads such as variable speed drives introduces harmonic currents that negatively affect transformer operation. So these harmonics increase losses, raise winding temperatures, accelerate installation aging, and reduce transformer lifespan if not properly managed. So the transformer performance under harmonic conditions can be evaluated using total harmonic distortion (THD), harmonic loss factor (FHL), and K factor methods. So in many real-world applications, transformer must be derated to remain within thermal limits specified by IEEE standard C59.91, with typical derating ranging from 15 to 25%. So the IEEE standard 1547 governs the interconnection of distributed energy resources and indirectly affects transformer loading through voltage, frequency, and power quality requirements. Together with IEEE standard C57.91 and C57.110, these standards provide guidance for managing harmonic effects and ensuring transformer reliability. Overall, successful large-scale PV integration requires proper transformer selection, harmonic mitigation, and adherence to relevant IEEE standards to achieve safe, efficient, and sustainable power system operation. So that's all from our group. Thank you.